Okay. Hello. Hello, everyone.
Yes, sir. We are live, sir. We can start.
We can start. Okay, fine. Hello, everyone. Purvansh, Sathik.
Sir.
Yeah. So you have any questions or anything that you want to discuss? Manojit, anybody? So I just want to hear from you. If you have any difficulties about the course, feel free to, come up with some questions. Yeah. Kushagra is here. Lakshmi Kanta. Okay. So if not, I think there were a couple of questions, right, guys? Jinal and Saurabh, they're here, I believe. So any questions from there that we can discuss? Let's get started with some basic questions. All right. Yeah. So there is one question that we have come across. One of the student was asking us, why are the atomic orbitals spherical? So anybody has some thoughts on it? So the question was, orbitals describe how the electrons are distributed, right? So the question was, why do you always think of these atomic orbitals as spherical? Is that the question, Gina?
Yes, sir, it was the same thing.
So the orbits or orbitals?
Sir, orbits and orbitals like that. Actually, okay. Yeah, like the student was actually, I think, considering a classical picture of 12th standard, considering circular orbits, yeah, spherical orbits. So
okay.
The question was, why not any other shapes? Like if it's triangular, square, what happens?
Okay, fine. So yeah, in the classical picture, you have basically a nucleus which is positively charged, and then the electrons go around the nucleus, right? The question was, I think, why is it always in circular, and why are we not taking triangles and things like that?
Yes, sir.
So one way to answer that would be symmetry, correct? So you are talking about an electron which is moving around. Even if you take a particle picture, there's an electron here, and there is the positive charge, right? There's a force of attraction. The force of there is a balance between, the electron tries to, as it moves, there's a centrifugal force, and there is some attraction which is holding it back. When there is a balance, it should really be in that orbit, right? That's the reason why, it usually goes in circular orbits. And at any point in the orbit, you experience essentially the same force, right? That's a stable orbit. And the de Broglie's picture we also discussed, wherein we said that, okay, if you think of this as a wave, there are integral multiples of these waves, right, going around on this. So like this, we have drawn this. When you have integral multiple of the wavelength, let's say if the wavelength of the electromagnetic wave is, let's say, in this case, electron, right, lambda e, integral times that should be equal to 2 pi the radius of the orbit, right? Wherever that relation is true, then that is the orbit which is allowed, right? So this is the classical picture. But if you look at the quantum picture, the electrons are not really particles, right? There is a probability of finding an electron around the nucleus. And is it possible to use? Okay, fine. So this is the probability, right? We talked about the solutions to particle in a box problem in the first week, wherein we said that if you have this sort of a potential and you have an electron confined to that, we have these different energy levels which are allowed, right? 1, 2, 3, and so on. They're of course not equally spaced. These solutions are allowed, correct? Now, the same thing holds even for a atom, but it's instead of this is a 1D potential well, right? Atom is a 3-dimensional potential well. So you have a strong nucleus in the center, and then the electrons are confined in a spherical space, right? So it's a 3D potential well problem. And if you solve it, you will get these discrete energy levels, which we call as 1s, 2s, and so on. 1s, 2s, 2p, 3s, like that, and just goes on, right? What are these? In chemistry, when we study, we think of them as, these are simply the orbitals, you have to remember them. But it's not true. If you actually look deeper, these are actually the solutions of the Schrodinger equation for a spherical potential well. And the wave function we told, right, it gives you the probability of finding an electron, correct? And so now in this case, the wave function will be in 3 dimensions. And in the case of an s orbital, the wave function is spherical in shape. Okay. When you go to a p orbital, the wave function becomes like a dumbbell. So there are 3 different dumbbells that are possible in the x, y, and z direction. That's why you get the px, py, pz. And then the d orbital is again, 2 dumbbells, and then you have various options in that, right? That's why you have more different shapes of orbitals that are possible. Okay. So when you say an orbital, s orbital, it means that you have a nucleus. There's an equal probability of finding an electron anywhere around the nucleus. That's an s orbital. So that has one. Let's say the first such state is called 1s, and so on. Okay. I don't know if that was too much information or what. Anybody wants to comment? Anybody has a question about that? Okay. All right. Does it answer, Jinal? I think we did, right?
Yes, sir. Yes, sir.
Okay.
This was the explanation.
I see. Yeah. All right. And then there was one more question, I believe. Okay, let me look up. Somebody had posted some questions just before this session in the Excel sheet I saw. There was something about. Okay, nice. Okay, they're coming here. So the first question, Jinal, you're seeing the sheet, Excel sheet that they shared?
Yes, sir. I checked that. One
Okay.
was on the emerging technologies about 2D materials.
Right. Okay. So Akshay was asking us, as a company, Intel was the first to introduce strained silicon, high-K dielectric, and most recently FinFETs into high volume manufacturing. But recently, Intel seems to have fallen behind in the pursuit of leading edge nodes against TSMC and Samsung. What are your thoughts and comments on this issue? Will it regain leadership? Okay. So, I mean, Akshay, it's very nice that you're following what is happening. Yes, in fact, recently, Intel seems to have lost at least the technological edge, but it is still very, soon to comment. We cannot conclude. I think Intel will again try to come back. The main issue Intel is facing right now is that TSMC has already introduced extreme UV into production. Okay. Extreme UV is basically one of the more advanced lithography nodes that enables them to pattern in very small dimensions. So far, I think if you look at the world over, the lithography machines are actually using a wavelength of 193 nanometers. We use what is called as 193 immersion lithography systems right now. And the next advance was, one of the next advances is basically 13 nanometer. And this is called as EUV, extreme UV. When you actually use a smaller wavelength to pattern, you get better, benefits. So TSMC has invested a lot in extreme UV, and that is why they seem to have got an upper hand. But we should never discount Intel. Intel, as you said, was a company that has introduced so much of advances, right? So we should never count out Intel. They will still come back. And in my view, this game is mostly about economics. Okay, as long as Intel retains the edge in terms of processor, I think they will be fine. The reason is, if you have a lot of money to pump in, you can always come up in technology, right? So I still believe that Intel is still, they can do a lot more, and they're also trying to diversify. Intel also wants to have some sort of a foundry. Previously, they have tried once in the past, but again failed. But recently, now they want to try it again. So just like TSMC, Intel also wants to make some of the technology available for others. So it should be possible. Yeah. Okay. That was Akshay's question. Akshay had another question, that is, with the advent and advancements of 2D materials such as MOS2 and WSE2, is silicon nearing its end? So again, the answer is, I think, no from my side, because silicon has been, material of choice for, I mean, it's an amazing material. It has many different benefits, right? So the silicon oxide is good, and it's a very well established material. The processing is very well established. So silicon, I think, will continue to be there for a long time to come. There are going to be some niche technologies, where this can be useful. But specifically about 2D materials, I think they still have to show that they are scalable and you can process a lot of transistors out of them. So far, what we are seeing is, in the laboratories, right, a little bit advanced, but not really production scale, right? Because we have many other issues. If you want to talk about MOS2, we need to have, let's say, a large area MOS2 without any defects. So we have techniques like CVD, which we use to grow MOS2, but they're not really at a mass scale yet. Okay, so there can be some niche applications, but I think still silicon, I would still not bet against silicon. Okay, for at least another 15-20 years. There will be technologies that will supplement silicon. Silicon has problems in terms of, the devices are now very, very small. Okay, so now increasingly people are looking at, how to get more out of it. So they're looking at system level alternatives. They are looking at how to package the chips, use an optical interconnect between chips and things like that. So some of these things are happening, and we'll see how it goes. Okay. Okay. Kushagra has a question, right? Jinal, Saurabh, Vinod, anybody, if you have any inputs or you want to clarify something, please feel free to just step in. Okay.
Yes, sir. Sure.
Anything you would like to add to what I said about MOS2 and WSE2?
No, sir. Actually, I think in the discussion forum also we answered the same way. It's difficult to
Okay.
like
I see. Okay.
meet the isolate the silicon.
Okay.
Other skill supplement.
Okay. All right. Okay. Shall we go to the next question? Okay. During the weekly live sessions, I got to know about the term equivalent oxide thickness. Okay, this is Kushagra, I think. Yeah. So the chances of getting more defects will increase in replacing silicon. Kushagra, I think you're on this call, right? Can you please clarify what this is? As thickness is somewhat large, to give same capacitance per unit area, what are the other parameters we see to realize this, like lattice matching? Well, I'm a little bit not okay. Okay, let me answer it this way. Okay, so for the benefit of everybody, we talked about equivalent oxide thickness. Okay, so did we talk about the MOS? We are in week 7, right? So we have discussed MOS, right? Metal oxide semiconductor devices. So in that, we talk about, let's say there is an oxide like this, silicon dioxide, and then bottom you have silicon. On the top you have, let's say, a metal, right? This is the structure we talk about, right? This is metal. And this is a substrate which is there all through. And we talked about this oxide, which is very, very critical. Did I talk about scaling? Did you already discuss scaling? All right. So we probably have not discussed scaling. Somebody looking at chats? No, if somebody is answering in that, I'm sorry. Are one of you looking at chat? How are the students?
Yes, sir. There are no messages yet.
No
in the chat
messages.
box.
Okay, fine. Okay. So yeah. All right. So in this case, what's happening is, if you have a silicon dioxide this way, over time, I think we have discussed so far that if you apply a gate voltage VG, there's going to be a capacitance, right? This is a semiconductor. In the top, you have a metal oxide semiconductor, right? So this is, we said it will effectively behave like a capacitor, okay, with one plate as a metal and the second plate as a semiconductor here, right? Okay, this is semiconductor, and in between you have an oxide which is an insulator. So now what happens to the charge? How is the charge related to voltage in a capacitor? Q equal to CV, correct? That we all know this. And so now if you apply, let's say, gate voltage, you want a charge, here. Let's say there's an inversion charge that forms here, correct? If you apply a positive voltage, you'll have an inversion charge which is negative. And you want to have more and more inversion charge in the case of MOSFETs, okay? Because that will increase the current. We like to have that when we scale MOSFETs. I think when you discuss MOSFETs in, I think, week 8 or 9, week 9, I think we start discussing MOSFETs, and I think scaling is discussed in week 10.
Scaling is week 10.
Week 10, right? Okay, yeah. In week 10, we discuss about the scaling, okay? So you'll understand more about it. But the idea is that if you reduce the thickness of the oxide, right? This is the thickness of oxide, Tox. The capacitance is given by epsilon of the oxide divided by the thickness of the oxide. Okay. So over time, we always try to reduce the oxide thickness so that the charge that you have, inversion charge, is higher. Okay. But it came down to a point, I'll discuss this again in week 10. Okay. It came to a point where this oxide became only 1 nanometer thick. Okay. What happens if you have 1 nanometer thickness of thick oxide? You can have some tunneling. Okay. So ideally, when we discuss MOS capacitor, right, we mentioned that the oxide is a perfect insulator. I think you'll remember that. So, but if you make the oxide very, very thin, it no longer behaves as a perfect insulator, but it starts leaking and you have some tunneling that happens. Okay. So to prevent that, in 2007, Intel used a technology, introduced a technology which is called as high K dielectric. So they replaced silicon. So after 2007, right, the MOS capacitor became like this. So you will have a high K dielectric, high K. Okay. And then there is a metal on top. Let's say this is a metal on top. So we went from regular geometry, which is MOS, metal oxide semiconductor, to metal high K dielectric semiconductor. This is a change that happened in 2007. Okay. The reason this happened was, if you introduce a high K, right? High K essentially means epsilon is higher. Okay. Epsilon of SiO2, we said, was 3.9, right? So there is a finite, capacitance associated with that. But if I take a high K dielectric, epsilon of high K, I think this I discussed, that is about 25, let's say. Okay. Then physically, I can have a thicker dielectric and still get the same capacitance. Okay. Is it clear? What is the capacitance? Capacitance is going to be epsilon of the oxide divided by the thickness of the oxide. Okay. In the olden technology, let's assume that it was 1 nanometer. You can immediately calculate what it is. 3.9 into 8.85 into 10 power minus 14 divided by, let's say, 1 nanometer, right? So 1 nanometer in centimeter will be how much? 1 into 10 power minus 7, right? This will be the capacitance of the oxide, let's say. Now, instead of 3.9 nanometer, sorry, 3.9, instead of this, make it 25. Okay. Then immediately you can increase the thickness. So you went from 3.9 into 25, 25 by 3.9. So you can actually. Gina, you have something?
Very good evening.
Sorry.
Good evening, sir.
Good evening. Yeah, who is speaking?
Thank you.
Good evening.
Yes, sir.
Who is speaking?
Good, sir. I just came.
Oh, you just came. Okay. Yeah, nice. No, you have any questions? You can, yeah, just let me finish this and then we can talk. Okay. So now you can have a thicker oxide, maybe something like 6 nanometers and so on. Okay. So with a high K dielectric, we were able to use a thicker oxide. But then in that context, we introduced the concept of equivalent oxide thickness, EOT. And that was the question. EOT is going to be how much now? The physical thickness of the oxide or high K, whatever you have. Physically, let's say T high K was some 6 nanometers. Okay. But it behaves as if it has a much lesser dielectric thickness electrically. It will be something like 3.9 divided by 25. So this is my equivalent oxide thickness that we were talking about. So the question in this context is, you're getting the you are increasing the thickness and getting the same capacitance. But what are the other parameters we see? I mean, will there be any lattice matching issues and so on? So Kushagra, in the context of lattice matching, right? Even in the case of oxide, you will not have lattice matching because amorphous silicon is silicon dioxide is amorphous, right? Silicon is crystalline. So there is nothing like a lattice matching between a crystalline and amorphous material. You don't have to worry about it. Okay. So even in the case of high K dielectrics, you don't worry about it. But of course, there are some other issues. Okay. That is, one of them is that when we talk about, let's say, silicon and silicon dioxide. Okay. Think about it. Silicon is a perfect crystal, right? Let's say there is silicon atom, silicon and so on. There is a lattice here, right? And then there will be some bonds here. Now, here you have SiO2, O, Si, some amorphous material, correct? So now it can happen that there's a bond here, there's a bond here, but there's a dangling bond here. It's not connected to anything. Okay. This I'll call it as a dangling bond. And if you have such dangling bonds at the interface, we call them as interface traps. Interface traps. Okay, these dangling bonds are not good for us. They actually make the current conduction lower. Okay, so but it so happens that if you have a silicon dioxide interface, the quality is very, very high. Okay, so very less interface traps interface trap density is very low for SiO2 interface. Okay, but if you have Si and high K dielectric interface, it can have more interface trap density. Because of that, there are some issues, but people have figured out how to solve them. They are not, they are not showstoppers. You can still continue to work with them. All right. So that is my answer. Does it answer your question or anything else that you want me to add? Okay. Samarth has a question. What are the differences between PN junctions and MOS? Why use MOS? Samarth, I hope you're here. All right. Just 1 second. I'm trying to. All right. Okay. Samarth's question was, why use MOS and not PN junctions? One of the critical difference between a PN junction and an MOS is that a PN junction is a two-terminal device, right? Okay. We don't really have much control. I mean, you can change the voltage and you get the current change that is there. But can I somehow switch off the current flow? For example, I have a terminal. Let's say I put a diode like this. I can control the voltage and then I can change the current. That's it. But keeping a certain voltage at A and B, I can't control whether the current flows or not. So in this context, an MOS device is very useful because it's a three-terminal device, correct? So you have the equivalently in an MOS case. Now I can basically treat this as a switch wherein I have my source, I have a drain. This I'm talking about a MOSFET, okay? MOSFET is slightly more advanced than MOS capacitor. MOS capacitor we have discussed, I think, in week 6, right? No, week 7 and 8, we are discussing MOS capacitor, but then we'll introduce MOSFET in the week 9. Okay. But essentially you have the third gate there, third terminal gate. When you apply a certain voltage, you can make the connection happen. Okay. When the gate is closed, current flows, right? Current flows when gate is closed. Gate is, on, let's say on, I'll say, okay, and off, okay, current does not flow, right? The opposite. Flow when gate is off. Okay. So we have this sort of a scenario. So this control we will not have in a PN junction. Okay. You have to also change the voltage in a PN junction. Whereas I can keep the same voltage. For example, I can keep this as ground 0, and this I can keep at 1 volt. Okay. Now, depending on whether my gate voltage is 0 to 1 volt, I can control whether the current flows or not. This is called the transistor action. For a transistor action, you need an MOS kind of a device. You can also have BJTs. Okay. BJTs are basically two back-to-back PN junctions. I didn't really discuss about this. I won't discuss about BJTs in this course. But there are certain places where you can actually use BJTs. You might have studied about, let's say, an NPN, right, transistor, wherein I have two PN junctions here. There's a PN junction here, and there's a PN junction here. So in this kind of a device, I can, I can connect one, to the base, and I can connect, you have emitter, you have collector, right? You can connect, apply some voltage, and again control the currents. Okay. We will not discuss that too much in this, but because I think, personally, I believe that the MOS technology is more useful practically. All right. So yes. So that's why having a 3-terminal device helps. Okay. Samarth, did I answer your question? Okay. All right. So Sagar has a question. Okay. The question is, why are the charge density diagram different for accumulation and depletion? Okay. Sagar, let's consider an NMOS capacitor. Okay. You're talking about, let's say, you have, let's say, metal. This is my oxide, and this is my P-type substrate. Okay. When will this be accumulated, Sagar? So accumulation means, if you have accumulation, ACC, I'll write it, that means accumulation. Basically, holes accumulate near the interface, right? Holes accumulate near interface. Why do we call it accumulation? Because what are the majority carriers here in the P-type substrate? They are the holes. When the majority carriers are at the interface, we call it accumulation regime. Okay. All right. So now, if you want to have holes here, I'll have to put a negative voltage here because this is a capacitor. So if I put negative voltage on the gate, I'll have positive charge. Correct? Does it make sense? So that is why when I draw the charge diagrams, I'll say that, okay, there is this like this, there is a negative charge here, and then there is a equal and opposite positive charge. So I'll say here minus Q, and this is plus Q when you have accumulation. Correct? Can somebody tell me if I can have a situation where I can have this, I can have a accumulation charge as Q by 2 and a gate charge as Q minus Q. Can we have this scenario? Guys, anybody wants to answer that? Kushagra. Okay. So this will not be possible because always if you have a capacitor device, you'll have a positive charge and then equivalent opposite negative charge, right? So this will not be possible. All right. So you can have this. So this is in the accumulation. So now why should, if you have a depletion region, what is different if you have depletion? Depletion means you are depleting the substrate of the, holes are depleted in the substrate or depleted in the substrate, right? What do we mean by holes are depleted in the substrate? What is the density of holes in the substrate? Saurabh, what will be the density of holes in the substrate?
It will be equal to the doping density.
Okay, yeah, the concentration will be equal to the doping density. Why do we say that? Like for example, this is a p-type substrate, right? Saurabh, why is this equal to the doping density?
So it's a p-type substrate. So
It's a p-type substrate, yes. So the hole density is basically given by Na, right?
yes, sir.
So now if I deplete the, can I have a scenario like this, Saurabh? Imtiaz, you're saying something? Imtiaz, your voice is breaking out. We are not able to understand. Maybe you just have to check your mic connection once, okay? Just try it and then speak. Can you try once more? No, I'm not getting, I'm not understanding.
Imtiaz, you can use the chat box also if you can.
Yeah. Chat box also will read. Yeah, Saurabh or somebody will read. Okay. Saurabh, now
Yes.
the question is, let me say I want to have this plus Q to be equal to 10 power 19. Okay. Or 18, I'll make it. Okay. I'll make it 10 power 18 per centimeter, per centimeter square. Okay. And now I want to create the same thing. The doping density is basically going to be, let's say 10 power 17. Okay. Can I have the depletion charge to be 10 power 18 here now? Minus 10 power 18, can I have it?
No, sir.
No, right? The reason is the charge, the space, the depletion charge is coming from the space charge, right? Why is the negative charge coming? This negative charge is due to uncovered acceptors. Correct?
Yes.
Now, if you want to have 10 power 18, then necessarily if I think of this as my substrate, right? If I draw a substrate in this form here, let's say I have some dopants here. Okay. My charge, total charge in the dopant, depletion charge is going to be, QD is going to be Na times what? The depletion region. Let's say if this is negative, right? Okay, I'll put it like this. The charge will be negative like this. You're going to have a depletion width. I'll call this as XD. So your depletion charge is going to be Q times Na times XD, the depletion width. Okay. It cannot be right at the interface. When I'm showing like this is right at the interface, in accumulation. Okay. But when you talk of depletion, it cannot be at the interface, but it has to be extending into the substrate. Right? So this is my depletion width. This is my XD. Okay. So now what is the depletion width, Saurabh? How much will be the depletion width? We can compute. We know that the total charge we want is basically 10 power 18, correct? 10 power 18. And the other side is basically doping density is 10 power 17. And then I'm just dropping the charge. Okay, coulombs is simply not required. So this is my XD. Okay, so it has to be 10 centimeters, which is never going to happen anyway. All right. Does it make sense, Saurabh?
Yes, sir.
Imtiaz, did he write anything on the
No, sir.
chat box? No. Okay. All right. I hope so why are charge density diagram for accumulation and depletion different? The main difference is in accumulation, the charge appears at the interface. At interface in accumulation. But in depletion, charge is distributed in substrate, in silicon, because the charge is coming from pushing away the holes, and the maximum charge you can get is only determined by the doping, correct? Think about it like this, okay? Let's say we are sitting in the classroom, and let's say a professor comes. Automatically, the front benches get empty, right? Because students want to always go into the back, correct? So if let's say you have to create more charge, okay, so think of that as a depleted. Professor comes in this is a positive charge. The student want to create that negative charge to balance. There's a capacitor, let's say there. So if let's say I bring in 10 units of charge, then 10 students have to go back. If you have to do that, the vacant spot is going to extend, because the density of the benches or the chairs is going to determine how much is the capacity, right? You don't have a situation where all the students are right at the front bench. You can't have it. They're distributed into the substrate. So now you can think of the students as a whole, and they're kind of going away, and that is causing your depletion charge. In this context, the depletion charge has to extend into the substrate. Okay, does it help? I hope it helps, Sagar. Sagar, if you're still unclear, you just just shoot us an email, and then we will directly talk to you one-to-one if required. Okay. By the way, this is valid for every one of you. You don't have to wait for live sessions. I think with 1 or 2 students, we already did this. So whenever you have questions, you just write us, and then we will answer it. Okay. If we are not able to answer it on the email, we will actually schedule a one-to-one discussion. It just takes 10 minutes for us. We are happy to do that. Okay. It's easier to discuss one-to-one. So you please email us, and then we will answer it. Okay. One of us will definitely get in touch with you. All right. So please, just interact. It's okay. It's a nice thing to interact. So you see, at least one of the things I believe, in learning is to ask questions. And somehow we seem to think that asking questions is wrong. No, ask me any question. Maybe I'll tell you I don't know. Or sometimes I'll tell you I know, whatever. Whatever I know, I'll tell you. If I don't know, I'll say that. So please, just don't hesitate in asking questions. We're not going to eat you. We're not going to do anything. There is nothing like, you have to get confident, right? How will you get confidence if you don't ask questions? Okay. So please feel free to approach us anytime. We are always happy to interact with you guys. And I mean, I don't know if you got it by now or not, but we are really passionate. All of us really like semiconductors. We think about it a lot. We discuss. So we are
Hello,
really
sir.
happy.
Hello?
Yes, Lakshmikanta, tell me. Yes, please.
I have some questions, sir.
Yes.
During MOSFET band bending, there is an oxide layer that you said it acts as an insulator.
Correct.
So how the charges flow through that insulator? If you are talking of band bending and charges flow, if you are given negative charge or a positive charge, so what is the insulator blocking those charges, or how charges are flowing through that insulator oxide?
Okay. So now essentially what is happening is, if you let's say take a case of a oxide like this. Okay, sorry. So there is a metal right on this side. So now we are saying that let's say we apply a positive charge. Let's take a p-type semiconductor. Okay. Initially, I'll take a p-type semiconductor like this, and this is my EV and EC, right? Now I apply a voltage. So this is my gates on this side. There is some gate. Okay. Well, let's assume that it's an ideal MOSFET. So the gate is here. Okay. Now this is my EF of the metal. Now, if I apply positive charge, what happens? Lakshmikanta?
So it's a p-type, hence there will be some positive, then there will be
Negative charge,
yes sir, negative charge will come at the interface.
right? So if you apply the band diagram, we write it like this. I mean, the band will look like this, right? When you finish, it will be like this. And then there will be, let's say there is some voltage here. In the bands will bend this way and the bands will bend. Of course, this is approximation, right? I'm just doing it roughly. All right. So this is my depletion region. Correct, Lakshmikant? XD, right? This is the depletion region. And your Fermi level in the metal goes down, EFM. This is my Q times VG, whatever it is. Okay. So now the question is, how do the charge flow you are asking, right? That is the question, right, Lakshmikant?
Yes sir, yes.
So now the idea is, this is a energy band representation. Physically, what is it? You have a silicon piece like this, and then there is an oxide maybe, and there is a metal like this, correct? This is MOS. Now, when you apply a voltage here, let's say I'm putting a battery like this. That's how the circuit finishes. Even if you have a perfect insulator, what happens? Now, this battery is essentially causing positive charge to appear on this side here, right? Eventually, the negative charge has to come from here, right? That has to be balanced. That means when you push away the holes, some holes are actually going in. That means electrons are coming in. You can think of it like that, right? You follow? Lakshmikant?
Yes sir, yes sir.
So eventually it has to, and we are not showing that connection. We are not showing the circuit finishing. But even if it's a perfect insulator, you are essentially taking away some electrons from here, right? You're taking away some electrons and you're putting some electrons in. You can think of it like that. Physically, there are holes which are moving here, but that's equivalent to electrons moving in, right? Holes moving out is equivalent to electrons moving in. Physically, that's what is happening. Does that make sense?
Yes sir.
Yeah. So that's what, and that is why we don't want this leaking thing. If you have an oxide which is leaking, then your transistor action is lost. 1 second. Huh? All right. Okay. Any other question, Lakshmikant?
Sir, during this band bending, will this band will for infinity, or will it stop at something?
Infinity. Okay. You mean to say that will the bands go like this?
Yes, yes.
No, it will not go. Eventually, it will be limited. It will not go very.
Thank you, sir.
Yeah. Why you think about it? Okay, a little bit. Because finally, it has to be a balance of charge. At some point, what will happen is, you see, I'll tell you the reason also, because we studied this. Let's say we created a depletion region in this case. Okay, all this we created as a depletion region. We put all of this negative. Okay, once you create some depletion region, what will happen? We studied that semiconductor always tries to come back to equilibrium, right? So in the depletion region, there will be electrons and holes produced to bring it back to equilibrium. It will try to come back to equilibrium. Okay, here electron hole pairs are produced. Okay, to bring silicon back to equilibrium. Okay, and now when the electrons and holes are produced, what is the direction of the field? We know that here the electric field is like this, here the electric field is like this. So the holes go into the substrate here. Okay, in this case, holes go into the bulk, and then electrons come towards surface, and that forms the inversion charge. So once you reach a certain maximum depletion width, your depletion region will not further increase. Okay, and that is why the band bending also further will not increase. So basically, the maximum depletion width is going to be XD maximum. Some maximum amount will be there. Beyond that, it will not increase. Okay, it cannot go to infinity. Does it make sense, Lakshmikant?
Yes, sir.
All right. No, yeah, if you have any questions, feel free to email, okay? Don't hesitate at all. We will be very, very happy to talk to you. I don't know if you guys realize, but semiconductors is so important in today's world. And we have to learn, all of us in India, we have to, now there is something called India Semiconductor Mission. The government is really trying very hard to actually bring in semiconductor manufacturing. Okay. The reason is, we all know that petrol we don't have, right? In India, we have to import petrol and we spend a lot of money for petrol. Now, even the imports for semiconductors, the chips and phones and all that we are buying, right? That is good. That is so much that we are spending precious foreign exchange. So the government is very, very serious about trying to make semiconductor manufacturing in India. Okay. You might have heard just yesterday, there was an announcement that Vedanta is a company that tied up with Foxconn and they're starting something in Gujarat. Similarly, there's something that is starting in near Mysore. In Hyderabad, there is something that is planned. So a lot of places people are trying to make them happen. And definitely, understanding people who understand semiconductors in a very, very deep way are very, very important. Okay. You might say that, I have, in this course, maybe I have taken a little bit more of physical insight because I don't like to teach, formulas. Okay, Vt equal to ln NAND by Ni square. I don't like to teach that kind of a thing. I like to go into intuition. Okay. So please, if you have any question, anything, it doesn't matter. It can be anything completely different. Okay. We'll be happy to answer. Okay. So did I miss any question, Jinal or Saurabh?
So there is one question.
Tell me.
Sir, Piyush wrote that he's getting a little confused with band diagrams for MOSFET under the influence of fields.
Okay.
So, is it possible for you to give a brief?
Okay. Piyush, I don't know what you're getting confused about, Piyush, because if I know your confusion, I can clear your confusion. Okay. But why don't you just shoot us an email, whatever time is convenient, from 9 to Saturday, Sunday, any time is also fine. Tell us, let us schedule a session where, roughly you give me a couple of hours where you're available, and then we will schedule a one-to-one meeting and we will go step by step. Okay. I'll answer it, for you. It's subtle, actually. It takes time. I understand. Even when I studied, I think I didn't understand the first time. So I don't blame you if you don't understand. That happens to all of us. I keep learning even now sometimes. Okay. There are always some subtle things there. But let us try to answer. Yeah, I'm happy to answer one-to-one. But let us assume, let's say, Saurabh, let's try to draw one band diagram. Okay. Let's take which one? Shall we try NMOS? Okay. Let's say we did this. No. There are some basic rules that I have highlighted, I think, in the lectures. Let's say this is my EF. And let's say this is my initial ideal MOS capacitor. Okay. And then there is a EF metal here. Correct? This is what we did. Now, the first rule you have to think about it. What is the direction of electric field? That is very important. Okay. The reason is that tells you how the bands will bend. For example, Saurabh, if I apply a positive voltage, how will the electric field be?
From metal to
semi. If I apply a positive here, positive gate voltage, if I apply, the field is basically, E is basically going to be in this direction from metal to semiconductor. Okay. And that I'll call as, okay, this way, right? This is my field in this direction. If I apply negative gate voltage, negative VG, right? E points from silicon to metal, correct? The field will be in this direction. Okay. So now if I apply positive bias, immediately I know that my oxide, if I have oxide has to bend, the bands will bend like this. This is positive direction, electric field. Okay. If I have negative electric field in this fashion, my field has to be like this. Right? This is Piyush, right? Yeah. Piyush, does it make sense how the oxide fields bend? These are oxide bands, correct? Similarly, silicon bands also will bend like this. Let's say if I start with a P-type semiconductor like this. This is initially my semiconductor, P-type. And if suppose the field in the silicon is positive, okay? Positive means going from left to right. Then how will the bands bend? Well, the bands have to bend like this. Okay. The important thing to remember is this gap is Eg, right? This has to be constant. Because just because you applied a field, the band gap is not going to change. All right. So this is the band bending. All right. This is for a positive E field, right? Or rather, the field is going in this direction, right? Positive field in silicon. Okay. If I have a negative field, what will happen? The bands have to go upward. Okay. The slope will be down, right? So in this case, if you have a negative field, you'll have like this, and then there is like this. Okay. So this is basically when you have field in this direction. Fields always, the bands always go upwards in the direction of increasing field. Okay. What is it? Did I say positive field? This one, right? This is negative field. Yeah. In silicon. All right. This is how bands will bend. Okay. Now, essentially, if you're trying to draw that, mass capacitor in depletion, you just have to think about it. So always, what is the recipe that I have given you? First, you take the structure, decide what is a charge. If it's a positive charge, it has to be like this, plus Q. Now there has to be opposite negative charge. How will that come? If it's a depleted capacitor, as a depleted semiconductor, you'll have this. This is my negative Q, right? So now how will the field be? The field is going to be in this fashion. That I know, right? This is the depletion. Now how will the bands be? Now the bands are going to be, look back at these pictures that I have drawn. One slide I will draw all of them, right? So there is this charge. Now, okay, just to show the balance, let me say like this. Now there's an oxide here. How to do this? Okay. There's an oxide, there's a positive field, so it goes like this. Okay. And then here you have a negative charge, but the field is still positive, right? Because there cannot be a situation like this. Electric field in silicon cannot be like this unless there is some special conditions. Okay. It's usually, you always see the scenario where electric field is like this positive here. This is wrong. Okay. Because it's depleted, you'll go like this. And there is a field here. There is a metal here. This is my EF of metal. This is my Q of Vg. And this is my whatever. Yeah. That's it. I have depleted a semiconductor. Okay. Piyush, you try the opposite one, we'll help you. Okay. If you are having difficulty, try accumulation. You try it by yourself once and then look at the slides. I have drawn those things on the slides. Then it will help clarify, I think. All right. Saurabh, did we miss anything else? I didn't hear Vinod's voice.
Sir, I am here.
You are there. Okay.
Yeah.
No. All right. All right. There's anything else that you have? I think we covered all the questions. Jinal, I think we covered all the 3 questions that you had, no?
Yes, sir, there was one more question in the Excel sheet.
Uh-huh.
Is it like because of the defects in the oxide region, the threshold voltage is lowered? So can we intentionally put some defects and lower the threshold?
Okay. The question was in this oxide, right? I mean, right now we have, this is actually going ahead. Let's answer it in the next time, Jinal, because I think this is not covered for everybody. When we talked about I think it will be better if you answer it next time. Next live session, we'll do one more week. Okay. One more time we will do next week. Okay.
Oh, okay, sir.
And when we do it, we'll answer this. The reason is, I think, I think everybody may not have covered up this thing. Let's give them a little bit of time so that they will cover up and then we will do it.
Yes, sir. Yes.
Who is the question? I mean, we can answer the student directly if we want.
Sir, Piyush, only the one who has asked about this band bending.
Okay.
Same student has asked.
One more. Okay. Yeah, Piyush. We just try to schedule a session with him. Just try. We'll just write a reply to him, and then we'll schedule, and then we'll try to, because I don't think he's there on the
Yes.
call.
Yes.
Yeah. We'll do it 1-to-1, so it's easier. Yeah.
Yes.
And the other thing I think he had was excited carriers relax down to the band edges. What's the importance of exciting them with the higher energy, deeper into the bands? So I think we are having a very nice spectrum of students. Some are learning, some are a little bit more advanced. So that's good actually. Yeah. So the reason, is you should also think about how the density of states changes. Okay. If you want to only have at the band edge, the number of states available will be very less. Okay. So if you come with, let's say, exactly the photon of band gap, right, then you will not be able to actually absorb much. It will transmit. Only when you have higher energy photon, then you can actually cause electron hole pairs. I mean, you can, you can actually make an electron go into the conduction band. Okay. So that's why it's important to actually go deeper into the bands. Yeah, eventually they'll relax back and then they'll emit us, another photon fluorescence. But it is necessary to actually come because the density of states at the band edge is very small. In fact, if you go to nanostructures like quantum wells and quantum dots, the density of states is higher at the band edge. So it helps actually in some way. Yeah. Anything else?
So like that question in the discussion forum was in the terms of the electrical properties, because generally when we apply electrical bias, that time also like electrons.
Oh, okay, okay.
They get more kinetic energy.
Yes. Yeah, when they get more kinetic energy, they have to go deeper into the bands. That's true. Yeah. Okay, I was thinking from the optical perspective. Yeah. So what was the question there? The importance of exciting them with a higher energy.
Well, like sir, because in the third week you discussed eventually they decay down to the band edge. So they were saying why we are putting more energy finally if they decay down.
Okay. So that means basically decay means your electron is accelerating, it gains energy, kinetic energy. When it hits something, it will come down in energy. It gets dissipated, the energy gets dissipated. So it's not like, we ideally would want it to go at a certain velocity. But yeah, it's something like, you have a less of traffic, you'll go at high speed, but suddenly you come to an intersection and then you'll stop. Your energy has to reduce. Okay, some scattering events happen and because of that you lose that. Otherwise, if you get too much of energy, then there will be collision and everything, right? There will be a lot of other secondary processes that happen. See, that's what, nature never really lets us go too far away from the equilibrium. We are always, we can push it to some extent, but if you go too far away, then something else that will happen. Okay, guys, anything else? Anything else came up in the live this thing? Okay, I think this was a very nice session. Let's try to do it next week again, because I think we didn't do for some time. That was my mistake. I'm sorry, I got too busy. But I'll try to come back, next week or 10 days. When, please, we will try to interact more. Okay. So for me as an instructor, the satisfaction comes only when I feel that you have understood it. Okay. So I'm always open to this. This is the most important thing I do. Okay. So yeah, I think that's it. I think from our side. Anything else you want to ask? If not, I think Balaji, can we close it? I don't know if Balaji is here. Guys, I'm just here. You can start signing out if you have no questions. Okay. Balaji? Balaji,
Sir, no.
can we sign out?
Can I? Yes, sir. Sure, sir. I will close it.
Yeah, please close it, then we'll sign it out. Yeah.
Okay.
Thank you.